Hello, grade 11 to 12. Welcome back to this lesson. Thank you very much for joining us once again. Today we're going to be continuing with Euclidean geometry, our revision, and we're going to be focusing on theorem number 5 and 6 of cyclic quadrilateral. Okay, let's start by revising what a cyclic quadrilateral is. Okay, so a cyclic quadrilateral simply it's a quadrilateral whose vertices lie on the circumference. Okay, as you can see, our point A is on the circumference, point B on the circumference, C and D also on the circumference. So that one is referred to as a what? As a cyclic quadrilateral. In other words, we can say A, B, C, D is a cyclic quadrilateral because A, B, C, and D are concyclic. That is, they lie on the circle, right? On the circumference of the circle. Okay, what is now not a cyclic quadrilateral? If you have something like this and maybe O, E, let's say F, H, like that. So OHFE is not a what? Is not a cyclic quadrilateral. And why? Is that although three of its vertices lie on the circumference, but there is one vertices that do not lie, that vertex that do not lie at the what? At the circumference. So for something to be called a cyclic quadrilateral, that it must be a quadrilateral where all its four vertices, they are lying on the what? On the circumference, and it's known as cyclic quadrilateral. Okay, let's now discuss theorem number 5. Okay, so theorem number 5 states that opposite angles of a cyclic quadrilateral are supplementary. It's a very quite fairly easy theorem, right? It's saying if you have a cyclic quadrilateral, you'll find that when you are adding the opposite angles, right, of that cyclic quadrilateral, they are going to be what? Supplementary. And what that does mean, and that means that they all add up to what? To 180 degrees. In other words, we can deduce that therefore, because A, B, C, D is a cyclic quadrilateral, as we can see, then we can deduce that opposite angles, when we add them, angle D plus angle B will be equals to what? 180 degrees. And also angle A, it's opposite to what? To angle C, right? Angle A and angle C, they will add up to what? To 180 degrees. By which reason? Opposite angles cyclic quad, right? Because we know that they are supplementary. Okay, very, very important. Let us now learn how we can prove this theorem, right? We just have a statement now, or rather theorem, that states that opposite angles of cyclic quadrilateral are supplementary. That is, they add up to 180 degrees, right? But very, very important, we need to prove this, right? So we are given that A, B, C, and D are the points that lie on the circumference of the circle, meaning that A, B, C, D is a what? Is a cyclic quadrilateral. Then we are required to prove that angle A and angle C is they add up to what? To 180 degrees, meaning that the opposite angles are supplementary, right? So how do we prove? So because we want to prove that this one and this one, they add up to 180 degrees, what you do is you construct a radius that passes through the other angles that you don't want to prove, right? So obviously we don't want to prove about D and B, but rather we want to prove that angle A and C is 180 degrees. So what we're gonna do is you construct a radius, and that passes through the other angles that you don't want to prove. It means that I'm just gonna join radius, this one, OB, and also another radius, what? OD, right? That is my construction. I won't write it down, but on the exam, if they ask you to prove it, you have to tell them what you did, right? For the sake of time, I won't write that down. So I can name this angle O1 and this one angle what? angle O2. Okay, so look at this. We have an arc, right, subtending an angle at the center here, right? The same arc subtending another angle at the what? At the circumference. What did we learn about that? Angle at the center is 2 times angle subtended at the what? At the circumference, meaning that our angle O1 is equals to 2 times angle what? Angle A. And our reason for that is that angle at what? At center is equals to 2 times angle at what? At circumference. Okay. So we also know, if we take it the other way around, we also know that this angle here, it's subtended by this arc at the center, right? It will be equals to what? The angle subtended at the circumference by the same arc. So it's gonna be angle O2 is gonna be equals to 2 times angle what? Angle C. And our reason is that angle at center is equals to 2 times angle at what? Angle at circumference. Okay, so what can we do now? We know that, but very, very important, angle O1 plus angle O2. What do we know about angle O1 and angle O2 there? Angle O1 and angle O2, what do we know about them? Remember, this is O1 and this is O2. These are angles around a point, right? They sum up to what? To 360 degrees. So by the reason angles round a point, angles round a point, angles round a point, right? They sum up to 360 degrees. Remember, we want to prove that angle A plus C is 180, meaning that we have to replace O1 by what? By 2 angle A, O2 by what? By 2 angle what? Angle C is equals to what? 360 degrees. Very, very easy now. To solve for angle A plus C, we can take out a common factor of 2. Then to solve for it, we divide both sides by what? By 2. Then we can finally deduce that therefore angle A plus angle C is equals to 360 divided by 2, which is what? 180 degrees. So that's basically how you prove that theorem. So to prove this theorem, remember this is theorem number 5, you use theorem number 2, which says angle center is 2 times angle at the circumference. And we already proved theorem number 2 from the previous session, meaning that this is actually correct to say opposite angles of a cyclic quadrilateral are what? Are supplementary. That is, they add up to 360 degrees. All right, let's now take a look at the converse of this theorem. And it is very, very important that you understand the converse of this theorem, because most of the exam kind of question come from the converse, right? So you must know the theorem. Obviously, opposite angles of a cyclic quadrilateral are supplementary. They add up to 180 degrees. But how can we now take the same statement and start with the last point to say, what if I just have something, a diagram now, right? It's not within a circle, but I'm saying that when I add opposite angles, I'm getting that they are all equals to 180 degrees, meaning that we can make that deduction from theorem 5 that, oh, this is actually a converse theorem, meaning that there's actually a circle around that quadrilateral, making it a cyclic quadrilateral. So this is very, very important for the questions that come to say, prove whether the following diagram, or rather whether the following polygon is a cyclic quadrilateral. So you have to be thinking of the converse theorem of cyclic quads, right? And this is theorem number 5. And how do we think about it? So the converse theorem states that opposite angles of a cyclic quadrilateral, if opposite angles of a cyclic quadrilateral are supplementary, right? It's sort of like a reverse now. Now, if opposite angles of a cyclic quadrilateral are supplementary, right, of a quadrilateral, not a cyclic quadrilateral, very, very important. If opposite angles of a quadrilateral are supplementary, then we can conclude that that quadrilateral is a what? Is a cyclic quadrilateral, meaning that there is a circle around it, right? Because opposite angles are what? Are supplementary. And this is the converse theorem. Okay, take a look at this diagram. Maybe the question say, prove that ABCD is a cyclic quadrilateral, right? Given a diagram like this, what can we do? We can check, we can prove by this. We can check, are opposite angles supplementary? When you take opposite angles, do they add up to 180 degrees? If you find that that is the case, meaning that that thing is a cyclic quadrilateral, there's a circle around that quadrilateral, because it's satisfying theorem number 5 to say opposite angles of a cyclic quadrilateral are what? Are supplementary. So from this point, we can see that angle D, when we take angle D plus angle B, we're getting theta plus 180 minus what? Minus theta. So theta minus theta is going to be 0. Then we'll be left with what? With angle D plus B is equals to 180 degrees. Therefore, we can conclude that ABCD is a what? Is a cyclic quad. Why? Because opposite angles are what? Are supplementary. So that's one of the ways in which you can prove whether something is a cyclic quadrilateral or not. Okay, let's quickly take a look at some examples to explore the theorem. Okay, so you are given 3 different diagrams. They want you to solve for the value of x and y, right? Okay, so let's start with the first diagram. This is our number 1. I'll name this number 2, and this will be our number 3. Okay, so in number 1, how can we solve? We can see that we have L, P, and M, and it lies on the circumference, forming what? What we know about forming a cyclic quadrilateral, right? Okay, what do we know? Opposite angles of a cyclic quadrilateral are what? Are supplementary, and that's theorem number 5. Meaning that to solve for x here, I can take these opposite angles and sum them up and equate to what? To 180 degrees. But the reason? Opposite angles of what? Of cyclic quad. Okay, so opposite angles of cyclic quad, we know that they are supplementary. Then x will be equal to what? 100 degrees. So that was quite very easy. Okay, so let's go to solve for y. Here's our thing here. So opposite angles of a cyclic quad are what? Are supplementary, meaning that 3y plus y, they will all add up to what? 180 degrees. So it will be 4y is equals to 180 degrees. Then to solve for y, we're gonna divide by 4 both sides, right? We divide by 4, then y is equals to what? 45 degrees. So that's actually how we can solve for that. Don't forget the reason here. Why are we saying 3y plus y is equals to 180? Because opposite angles of what? Of cyclic quad. Opposite angles of cyclic quad, we know that they are supplementary. Okay, let's do number 2. Okay, so for number 2 also, they want you to solve for x and y. It's quite a relational understanding approach question, where you also have to relate to other theorems that we learned in the previous sessions. Okay, so how can we solve for y? Look at this AD here. Can you see that AD is a diameter? What do we know about a diameter? Angle subtended by the diameter at the circumference of the circle is a what? It's a right angle, meaning that our y is equals to what? 90 degrees, because this is a angle in what? In semicircle. Angle in semicircle, or someone can say angle subtended by a diameter. Okay, so that was quite easy. Let's go and solve for x now. Okay, how can we solve for x? Look at this diagram here, A, B, C, D. It has its 4 corners on the circumference, meaning that it is a what? It is a cyclic quad. What do we know about cyclic quad? That opposite angles of a cyclic quad, it's opposite to that one, right? Opposite angles of a cyclic quad add up to what? To 180 degrees, meaning that x plus 50 degrees is equals to 180 degrees, because opposite angles of what? Of cyclic quad. Okay, so to solve for x, we're just gonna transpose and our x will be equals to what? 130 degrees. So x will be equals to 130 degrees there. Okay, so let's lastly go and solve for z, because there is also z there, right? How can we solve for z? We have 90 degrees here, we have 50 degrees here. So obviously we can use this triangle and add up the angles and equate to 180, because we also know that some angles of a triangle, they all add up to what? To 180 degrees. So meaning that our z plus 90 plus 50 will be equals to what? Will be equals to 180 degrees, because of what? Some angles of a what? Of a triangle. Okay, so our z will be equals to 180 minus 90 minus 50. Okay, so which will be what? 40 degrees. Okay, let's quickly look at number 3. Okay, so for number 3, they also want you to solve for x and y. How can we solve for x? How can we solve for y now? Okay, very interesting. You have parallel lines. Can you see that this line is parallel to this one? What comes to your mind when you think of when you see parallel lines? There are 3 things that must come, right? Do we have alternating angles? Do we have corresponding angles? Do we have co-interior angles? And the ideas that comes with those kind of thinking. Okay, so to solve for y, we can look at something here. Okay, look at this shape here. It's forming sort of like a U, right? Meaning that we have co-interior angles. What do we know about co-interior angles? Co-interior angles add up to what? To 180 degrees. So they are supplementary. And this is because what? Co-interior angles, right? And also we have to tell them the lines that are parallel. AO is parallel to what? To BC. Okay, we can go and solve for y now. Y will be 180 degrees minus 150 degrees. And our y will be what? Will be equals to 30 degrees. So your y there is 30 degrees. Okay, let's go and solve for x. Okay, so for x, so this is quite a little bit tricky, as most of you might make a mistake of thinking maybe this is a cyclic quad. Some people can say 150 plus x is equals to 180, which is totally incorrect, right? Because this is not on the circumference, meaning that AOCB is not a cyclic quad. So how do we solve for x now? That is on the circumference. We have the angle at the center, right? We have to be thinking of theorem number 2 to say angle at the center is 2 times angle at the what? At the circumference. Okay, so meaning that we have to get this angle this side, the one at the center subtended by this arc, right? How can we get it? So I can just name it angle O1. So we can say angle O1 plus 150 must be equals to what? Or rather, let's name it angle AOC plus 150 must be equals to 360 degrees, because these are angles around a what? Around a point, right? Angles around a point. So angle AOC will be equals to what? 3 sig is t minus 150, which will give us what? 210 degrees, right? So this angle here, it's 210 degrees. Now it's quite simple to solve for x. How can we solve for x? 210 degrees, angle at the center is 2 times angle at the circumference, which is x there. So angle at center is equals to 2 times angle at circumference. Okay, so we can solve for x by dividing both sides by 2, and our x will be equals to 210 divided by 2. Okay, so which will give us what? 105 degrees. So you can see that when solving questions related to Euclidean geometry, we are not limited to one theorem. You have to be thinking of all those theorems that we have been covering in the previous session, and use a relational understanding, relate them to the question that you are given. Okay, so long as the necessary conditions are met in your diagram. Okay, let's kindly now go and explore another theorem. Okay, let's now explore theorem number 6 of cyclic quads. Okay, so it says and if you have a cyclic quadrilateral and you have an exterior angle, what will happen is that that exterior angle of a cyclic quad will be equals to the opposite what? Interior angle. And we give a reason exterior angle of a cyclic quad. Okay, so what do we know? Exterior angle of a cyclic quad will be equals to the opposite interior angle. So theorem 6 state that an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle, right? So and that's your theorem about cyclic quad. It's theorem number 6. Okay, let's quickly prove this. So if you're given that ABCD are the points that lie on the circumference, we know that ABCD is a cyclic quad, right? So we are required to prove that angle C1 is equals to angle A, right? So we want to prove that angle C1 is equals to angle what? Angle A. So in order to prove this theorem number 6, you use actually theorem number 5, right? You use theorem number 5. And what do we know from theorem number 5? We just proven that opposite angles of a cyclic quad are what? Are supplementary, meaning that we can deduce that angle A plus angle C2 are equals to what? Are equals to 180 degrees, right? Because these are what? Opposite angles of what? Of cyclic quad, right? We know that they are supplementary. Okay, so we can just go and solve for C2, right? Because we don't want C2 in something that we want to prove, right? So C2 is equals to 180 degrees minus angle what? Minus angle A. Okay, so we can name that as our equation 1. But we know something. But we know that angle C2 plus angle C1 are equals to what? 180 degrees. Can you see these angles there? They're equals to 180 because these are some angles of a what? Of a straight line, right? We know that some angles of a straight line, they sum up to what? 280 degrees. Okay, so meaning that we can come now and replace C2 by what? By angle 180 degrees minus angle A, right? Plus what? Plus C1 is equals to what? 180 degrees. So what we did, where there is C2, we just replace what C2 is equals to, which is 180 minus angle A, right? Then we can take 180 minus A to the other side. Then we'll have C1 is equals to 180 minus 180 plus angle A, right? Yeah, plus angle A. So 180 minus 180, they cancel. Then we have finally proven that indeed an exterior angle of a cyclic quad C1 will be equals to the opposite what? The opposite interior angle. Okay. All right, so before we look at an example, let's look at the converse theorem. And very, very important, like I said, when we're doing converse theorem of theorem number 5, this is very, very important because they can give you this kind of diagrams, right? And there are no circles within them, any quadrilateral, and without being even inside a circle, or rather, they can be inside a circle most of the time, but not all their vertex being on the circumference. And they can want you to prove that this is a cyclic quad, right? You actually use the converse theorem, right? So the converse theorem, theorem 6, state that if you find that you just have your quadrilateral where you have an exterior angle being equals to the opposite interior angle, right? Then you can deduce that this is actually what? This actually lies inside a circle, meaning that is a cyclic what? Is a cyclic quad. So long as you are seeing that an exterior angle is equals to the opposite interior angle, you can deduce that, oh, actually this is a what? This is a cyclic quad. So in this case, we have just been given that angle C1, or rather they wrote it down for you. Angle C1 is equals to angle A. Then we can conclude, therefore, ABCD is a what? Is a cyclic quadrilateral, because the opposite angle is equals to the opposite interior angle. Okay. Okay, let's quickly take a look at an example. Okay, so this is our number 1 and this is our number 2. They want you to solve for x and y. Okay, so can you see that DEFG is a cyclic quad, right? And it has some exterior angles here, right? What can we deduce? Exterior angle of a cyclic quad is equals to opposite interior angle. Exterior angle of a cyclic quad is equals to opposite interior angle. So it's quite very simple to solve for that, right? Knowing the theorem, we can deduce x is equals to what? 88 degrees. Because what? Exterior angle of what? Of a cyclic quad, right? And also y will be equals to what? 105 degrees because of what? Exterior angle of a what? Of a cyclic quad. We know that exterior angle of a cyclic quad is equals to opposite interior angle. Okay, let's move to diagram number 2. They also want you to solve for x and y and also for z, right? And also for z. Take a look at this. So this is also a cyclic quadrilateral. EDCB is a what? Is a cyclic quadrilateral, right? Meaning that, and we can see that there's an exterior angle in that cyclic quad, right? What can we deduce? Exterior angle of a cyclic quad is equals to opposite what? Opposite interior angle, meaning that our x will be equals to 125 degrees by the reason exterior angle of what? Of cyclic quad. Okay, so we can replace x by 125 degrees. Let's go and solve for y. How can we solve for y? We have to use relational understanding. Remember theorem number 2. If you have a diameter, the angle subtended by the diameter at the circumference is actually a what? A right angle, meaning that our y is 90 degrees because what is an angle in what? In semicircle, or at the angle subtended by diameter at the circumference. Okay, we have to solve for z now. How can we solve for z? It's quite very simple. If you take a look at this triangle, right, you see that you have an exterior angle of a triangle. We also know that the exterior angle of a triangle is equal to the sum of the two opposite interior what? Interior angles, meaning that we can say 125 degrees is equals to z plus what? 90 degrees, because we already gotten y as 90 degrees. And we just say exterior angle, what? Angle of a what? Of a triangle. So we know that from the geometric basics that we did in session number 1. Okay, so z will be equals to 125 degrees minus what? Minus 90 degrees. Okay, so 125 minus 90 will give us what? 35 degrees. So that's actually how you can solve this using this theorem and some of the geometric basics. Okay. All right, this marks the end of our session. Thank you very much for joining. Thank you very much for watching. We were doing theorem number 5 and 6 of cyclic quad. Coming up next is theorem number 7 and 8. Okay, keep watch for it. And otherwise, that's all for me. And goodbye.